Hello everyone. This lesson is on propagation of uncertainties. We've seen what errors in experiments are. They are things that make a result different from the true value. And they come in various kinds like zero error and parallax error. They're one of two types, random or systematic. And the uncertainty is the size of the error associated with a measurement. Propagation of uncertainties is all about how you combine uncertainties from measurements to come up with an uncertainty on a calculated quantity. In order to estimate the uncertainty in a calculated value, we need to be able to combine uncertainties correctly. So let's have a quick look at our terminology again, our symbols. So let's say we have a value a, variable a, that has a value a0, and it's plus or minus delta a. So this is the value, this is its absolute uncertainty. Its absolute uncertainty is delta a, which is this part here in front of with the plus or minus in front of it. The value itself being a0. The fractional uncertainty is the absolute uncertainty over the quantity. The percentage uncertainty is that thing times 100%. So as an example, here is a value of a length, 28.3 centimeters with an absolute uncertainty of 0.4 centimeters. So that's the absolute uncertainty. The fraction is 0.4 over 28.3, which is 0.0141. And the percentage uncertainty. You will note that the absolute uncertainty is expressed to one significant figure, but that we've expressed both of these to two significant figures because we're allowed to do that because we tend to keep an extra one for guard digits in a calculation. And at the end, we convert everything back to absolute uncertainties, round it to one significant figure, and then round the quantity itself to the same number of decimal places. Addition and subtraction of quantities. So if you have something and it's made up of two parts either added together or subtracted from one another, and each of those parts has an uncertainty, you can calculate the uncertainty on the sum or the difference. So let's say we have a quantity Q, which is A plus B, or equivalently A minus B. In all cases, the absolute uncertainty in Q is the sum of the absolute uncertainties in the bits of which it's made of. So in this case, A plus B minus C, the absolute uncertainty in Q is the absolute uncertainty in A plus the absolute uncertainty in B plus the absolute uncertainty in C. Now it's always plus. We never cancel out uncertainties. Uncertainties only ever get bigger. So here we have it with the deltas. Delta Q is the absolute uncertainty in Q. So that's equal to an absolute uncertainty in A plus the absolute uncertainty in B. Let's take an example. The side A of a square is measured to be 12.4 plus or minus 0.1 centimeters, and we're asked to find the perimeter of the square. Well, the perimeter of the square is going to be 4 lots of that side added together. So, if the absolute uncertainty in the length of one side is 0.1 centimeters, and we add this together to itself 4 times, then we're expecting the absolute uncertainty in P to be 0.4 centimeters, which it is. If we're finding the percentage uncertainty in the quantity A minus B, where this is A and this is B, then we're going to have something quite interesting. Now you'll see that A is very similar in size to B. So when you take A minus B, the value is going to get really small. But remember that the uncertainties only ever get bigger. So the absolute uncertainty in Q is going to be 0.3 plus 0.5. So the absolute uncertainty in Q is going to be 0.8 by comparison with this small number. And so the percentage uncertainty is going to get quite big. The calculated value is 1.4, so that minus that must be 1.4. The absolute uncertainty is 0.8, so Q is 1.4 plus or minus 0.8. The fractional uncertainty becomes 57%. Now 0.3 is a tiny, teeny weeny fraction of A, and 0.5 is a similarly minuscule fraction of B, but the quantity A minus B has a really large percentage uncertainty. Multiplication and division. This is where it starts getting slightly different. In addition and subtraction, we are always adding the absolute uncertainties. For this next bit, we're always going to be adding the percentage uncertainties. Here, the fractional uncertainty of the result is the sum of the fractional uncertainties of the quantities involved. The fractional uncertainty is just the percentage uncertainty divided by 100%, so they're the same thing. So here we go. If Q is A times B, the fractional uncertainty on Q, which is delta Q over the value of Q, is the fractional uncertainty on A plus the fractional uncertainty on B, which is delta A over the value of A, delta B over the value of B, and if you want, you can change all of this into percentages by timesing both sides by 100%. And it's the same for division. We're always adding the fractional uncertainties, and in the slightly more complicated case, we're multiplying all these quantities together, we're still adding the fractional uncertainties, and we're still adding the percentage uncertainties. Here's an example. The sides of a rectangle are A and B. Find the area, capital A, of the rectangle. We're going to multiply those two quantities together. So we can do 5 times 2.5, which will give us the value of the area. Then to get the percentage uncertainty, or the fractional uncertainty, on the area, we're going to need the fractional uncertainties on A and B. Fractional uncertainty on A, 4%. Fractional uncertainty on B, 2%. So the fractional uncertainty on the area is the sum of those. 4% plus 2% is 6%. We can do the area, 2.5 times 5, so that's the two quantities times together, is 12.5 square centimetres, with an uncertainty of 6%. So now we have to convert that back to an absolute uncertainty, because we want to be able to quote the value with a plus or minus. So if the fractional uncertainty is 0.06, then you can find out that the absolute uncertainty is 0.75 square centimetres. So A is 12.5 plus or minus 0.8 centimetres squared. You'll note, as usual, that the absolute uncertainty is rounded to one significant figure, and then the decimal places are made to match in the value. Powers and roots. The rules for powers and roots follow neatly on from the rules for multiplication and division. So let's have a quick example. Let's say Q is A cubed. Well, the fractional uncertainty on Q will be equal to the fractional uncertainty on A plus the fractional uncertainty on A plus the fractional uncertainty on A again, because Q is A cubed, which is A times A again times A again. So this is 3 lots of fractional uncertainty on A. Whoops, zero's in the wrong place. There we are. So if Q is A cubed, the fractional uncertainty on Q is 3 lots of the fractional uncertainty on A. Let's also then think about, just deleting that, let's also think about some ways of expressing powers. So if we have, I can't seem to get rid of that for some reason. There we go. A to the 1 over 3, what does that mean? Well, that's the cube root of A. And if we have A to the minus 3, what does that mean? That is A to the 1 over A cubed. So when we have quantities which have been either cube rooted or are 1 over some power, what we do is we translate them into a power which is either fractional or negative, and then we can use this rule. So the fractional uncertainty of the result is the fractional uncertainty of the quantity multiplied by the absolute value of the power. When it says absolute value of the power, it means that this minus doesn't come into play. If Q is A to the minus 3, the fractional uncertainty on Q is 3 lots of the fractional uncertainty of A, not minus 3 lots. So here's the rule. If Q is A to the power of n, then we have the fractional uncertainty on Q is n lots of the fractional uncertainty on A. This modulus sign here is just saying get rid of the minus sign if there's a minus sign. We have nth roots, so if Q is the nth root of A, then you can express roots as powers. So if the nth root of A is A to the 1 over n, so the fractional uncertainty in Q is 1 over n times the fractional uncertainty on A. Let's have a look at an example. A mass is measured to be 4.4 plus or minus 0.2 kilograms, and its speed is measured to be 18 plus or minus 2 meters per second. Find the kinetic energy of the mass. So what do we need? Well, firstly, we can calculate the kinetic energy. That's easy enough. I just need to turn this back into a pen. The kinetic energy is, we know, a half times the mass times the speed squared, which is 0.5 times 4.4 times 18 squared, 712.8 joules. Now, to work out the fractional uncertainty on the kinetic energy, we're going to need the fractional uncertainty on the mass and the fractional uncertainty on the speed. So, or the percentage uncertainties on those things. Let's work out the percentage uncertainty on the mass. So we've got the uncertainty in the mass over the mass is 0.2 over 4.4. Which is 0.045, or round, because we can keep 2 decimal places, we're going to have 4.5%. For the speed is 2 over 18, which is 0.11 or 11%. So we've got the percentage uncertainty on the kinetic energy is going to be the percentage uncertainty on a half plus the percentage uncertainty on m plus the percentage uncertainty on v squared. What's the percentage uncertainty on a half? Well, it doesn't have one. It's a number. It's not a measurement. It's just the number 0.5. So we can ignore that. So what we're after is the energy, delta E over the value of E, is delta M over the value of M plus 2 lots of delta V over the value of V, i.e. 4.5% plus 2 lots of 11% is 22%, which is 46.5, but again 2 sig figs, so we're going to round it 26.5. We're rounding it to 2 sig figs is 27%. So let's put the answers up. Kinetic energy is a half mv squared, so we've got the right value of the kinetic energy. We've got the formula that we've just written down there. That's wrong. That should be a plus. There we go. 0.267 or 27%. If we have the kinetic energy, which we do, and we have its uncertainty, which we do, it's 27%, we want to be able to express this as some number plus or minus some number with the same unit. So we need to convert this 27% back into an absolute uncertainty. I'm just going to get rid of that so you can see slightly better. So the absolute uncertainty, so what's 27% of 712.8? It's 190.8 joules. Remember, we are keeping only one significant figure for an absolute uncertainty, so this is rounded to the nearest 100 joules. So this is delta E is plus or minus 200 joules. And since we're rounding this to the nearest 100 joules, we've got to be rounding this, the energy itself, to the nearest 100 joules. So this is going to be 700 plus or minus 200 joules. So 700 plus or minus 200 joules, or 7 plus or minus 2 times 10 to the 2 joules. Another example, let's take the quantity Q, which is 3.4 plus or minus 0.5, presumably some quantity without a unit, and we're going to calculate the uncertainty in 1 over Q and in Q squared. When they say uncertainty, it's implicit that they're meaning absolute uncertainty. So let's calculate the fractional uncertainty on Q first. Delta Q over Q naught, the value on Q is 0.5 over 3.4, which is 0.15 or 15%. So we can calculate the uncertainty in 1 over Q. Firstly, we need the value. What is 1 over Q? 1 over Q is 1 over 3.4, 0.29. And let's find the uncertainty in Q, the value of Q squared while we're here. That is 3.4 squared, which is 11.56. Now, we want to convert the percentage uncertainty in Q to this. What's 1 over Q? Well, it's Q to the minus 1. So we know the percentage uncertainty on Q is one lot of the percentage uncertainty on Q. That's not terribly helpful, but it just means that as opposed to, let's say Q was A squared again, the uncertainty on A would come in twice, because the uncertainty of A was going to be 2 lots of the uncertainty in Q is going to be 2 lots of the percentage uncertainty on A. Well, here we've got this thing, which is 1 over Q. The percentage uncertainty on 1 over Q is going to be the modulus of minus 1, so 1 lot of the percentage uncertainty on Q. So actually, this is going to be plus or minus 15% for 1 over q. And q squared, well, it's going to get 2 lots of that, so that's going to be plus or minus 30%. So let's look at that. So we've got 1 over q. The fractional uncertainty, this is saying that the fractional uncertainty in, let me turn this back into a pointer. Well, fractional uncertainty in 1 over q is the same as the fractional uncertainty in q, which is what we've said here. So 15%. So the absolute uncertainty in 1 over q is going to be 15% of the value of q. 15% of 0.29, which is 0.04325. Remember that we're only keeping one sig fig here, so this is going to be 0.04. And because we've rounded this to the nearest hundredth, this has got to be rounded to the nearest hundredth. So this is 0.29 plus or minus 0.04. Now for the next one, we've got q squared. The percentage uncertainty on q squared is going to be 2 lots of the percentage uncertainty on q, which is, as we've said, 30%. We want the absolute uncertainty, so what's 30% of 11.56? In this case, it's 3.4. Again, rounding, this is going to be plus or minus 3. And if this is rounded to the nearest unit, this must be rounded to the nearest unit, so this is 12, plus or minus 3. Okay, another example. We have the volume of a cylinder of base of radius r and height h is given by volume is pi r squared h. Now that we've been told the volume is measured with an uncertainty of 4% and the height with an uncertainty of 2%, so we want the uncertainty in the radius. Now, the first thing we've got to do is we've got to rearrange this equation for r. So pulling, I've turned it into a laser pointer, hang on, pen. V is, well, V over pi times h is r squared. So r is the square root of v over pi h. Alright, so what we're going to do is we're going to find the percentage uncertainty on r. Percentage uncertainty on r, I'm going to give this a new symbol. I'm going to call it uncertainty percentage r. There we are. Is going to be, well, it's whatever this thing in the square root is to the power of a half. So it's going to be half as much as what's in the bracket, which is the percentage uncertainty on v, plus the percentage uncertainty on pi, which there isn't one, plus the percentage uncertainty on h. That's going to be a half of 4% plus 2%, which is 3%. So they've solved for the radius. The uncertainty then is going to be half as much as the percentage uncertainty on v over pi h, which is 3%. Uncertainty in other functions. The mathematical functions we've discussed so far are addition, subtraction, multiplication, division, and raising to powers. There are other functions which you're going to need, like exponentials and logs, and trigonometric functions. To deal with those, we're not going to need a whole slew of separate rules, we're just going to brute force it. So let's start off by remembering what an error bar is. An error bar shows a measurement in the middle, and it's twice as long as the uncertainty because it goes down to the value minus the uncertainty and it goes up to the value plus the uncertainty. And what we're going to do is we're going to apply the function to the error bar, to all 3 points of it, and our new uncertainty is going to be half the range. So let's have the example. T is 1.3 plus or minus 0.1 seconds, and we want to calculate the log of t. So let's have a look at this error bar here. We can express t as 1.3 in the middle, and the true value is anywhere between 1.4 and 1.2. And we want to calculate the natural log of this, so we do the log. Log of 1.2 is 0.182, log of 1.3, 0.262, and log of 1.4 is 0.336. So here we've got a range, and we know that we can express an uncertainty as a half a range, as an estimate. So here it is. The uncertainty in log of t is the maximum value minus the minimum value over 2. So in this case, rounded to 1 sig fig, 0.08.